For years, the number was 2 trillion. 2 trillion galaxies stitched into the fabric of the observable universe, and we thought that was the final count. Then James Webb turned its mirror toward the deepest dark and saw something underneath, a layer we were never supposed to see. Tonight we trace what it found and why it quietly rewrites everything. Before we drift in, gently like the video and subscribe so these long, calm journeys keep finding you. And tell me softly, where in the world are you listening from, and what hour is glowing on your clock right now? Two trillion. Let that number sit in the room with you for a moment. Not 2,000, not 2 million, not 2 billion, 2 trillion. If you tried to count them one per second, without sleeping, without pausing, without ever looking away, you would need something in the neighborhood of 63,000 years. Whole civilizations would rise and fall in the time it would take you to finish counting galaxies. And every single one of those galaxies, every one, would contain hundreds of billions of its own stars, its own suns, its own quiet planets circling in the dark. That was the number we lived with. 2 trillion galaxies in the observable universe. It was the settled answer, the one that appeared in textbooks, the one that scientists cited on stage, the one that felt, for a while, like the final count. Tonight, we are going to take that number apart, gently, carefully, and we are going to replace it with something stranger. Because a few months ago, James Webb turned its mirror toward one of the darkest patches of sky we know, held it there in silence for hours, and came back with an image that quietly rewrites the shelf of light itself. Not the bright galaxies at the top, not even the faint ones we already knew about, something beneath them, a layer we were never supposed to see. I want you to settle in for this one. Whatever room you are in right now, wherever you're listening from, let it get quieter. Let the temperature of your thoughts drop just a little. Because the story we are about to trace is not just about a bigger number. It is about what a bigger number does to the rest of the timeline. Every calculation we ever made about when the last star will burn, when the last galaxy will dissolve, when the last black hole will finish evaporating into the void, was built on top of that older count. And once the count changes, the timeline changes with it. So tonight, we are going to walk from that number all the way forward to the end. To understand why 2 trillion was ever the answer, you have to go back to a small square of dark sky and a stubborn choice made almost 3 decades ago. In the mid-1990s, a director of the Hubble Space Telescope named Robert Williams made a decision that many astronomers thought was reckless. He pointed the telescope at what looked like a completely empty patch of sky, a tiny black square roughly the size of a grain of sand held at arm's length, and he told it to stare. Not for a moment, not for a night, for days. Hundreds of separate exposures stacked on top of each other, patiently gathering photons from a region that, to the naked eye, contained nothing at all. When the image finally came back, that black patch was not black. It was crowded. Thousands of galaxies, faint smudges of every color and shape, packed edge to edge like grains of sand on a beach. That image became known as the Hubble Deep Field, and then later the Hubble Ultra Deep Field. Deeper exposures, longer stares, more faint smudges pulled out of the dark. Each version peeled the sky back a little further, and astronomers realized something important. If a random empty patch of sky contained thousands of galaxies, and if you assumed the universe was more or less the same in every direction, then you could take the count from that little square and multiply it out across the entire sphere of the sky. That is how the estimate of 100 billion galaxies first became a number people trusted. Then, in 2016, a team led by an astronomer named Christopher Consulis took that reasoning further. They looked at every galaxy survey ever done, at every depth, at every distance, and they noticed something. The deeper you looked, the more galaxies you found per unit of sky, and the ones you found in the distance were smaller than the ones nearby, which meant, if you followed the logic, that the early universe had many, many more small galaxies than we could actually see. Most of them were simply too faint, too dim, too far, too small for even Hubble to register. So the team did the math. They extrapolated. They asked, if the trend continues, how many galaxies must there really be, including the ones we cannot yet detect? And the answer came back. 2 trillion. Roughly 10 times more than we had ever counted directly. For years, that was the story. 2 trillion galaxies in the observable universe, most of them invisible to us, most of them assumed, most of them living in a region of the light spectrum that no telescope of that era could reach. That is where James Webb comes in. I want you to picture the mirror first. It is not a single smooth disk like older telescopes. It is a honeycomb. 18 hexagonal segments made of beryllium and coated in a whisper-thin layer of gold, arranged into one great golden flower 6.5 meters across. Gold, because gold reflects infrared light better than almost any other surface we know how to make. And infrared, because that is the light Webb was built to see, not the light our eyes know, the older light. The light that has been traveling for so long, across a universe that has been quietly stretching the entire time, that its wavelengths have been drawn out and drawn out and drawn out until they slipped past the red end of the visible spectrum and into the invisible warmth beyond it. Every galaxy in the early universe emits its light in what would look, to a nearby observer, like the ordinary colors of hot young stars: ultraviolet, blue, white. But by the time that light has traveled across billions of years of expanding space to reach us, it has stretched, it has cooled, it has slid down the spectrum until it arrives at our instruments as infrared, which means the earliest, faintest, most ancient light in the universe is simply not visible in the wavelengths that Hubble was designed to see. It slips right past. Webb was built to catch it. That golden mirror, folded up like origami inside a rocket, launched into space on Christmas Day of 2021, unfolded in the dark 1,000,000 miles from Earth, and cooled itself down to a temperature so low that its own warmth would not drown out the whisper of ancient photons arriving from the beginning of time. That is the eye we are working with now. An infrared eye, colder than almost anything else in the solar system, staring quietly into the deep. And when we pointed it at the same kind of dark, empty patch of sky that Hubble once stared at, something happened that we did not entirely prepare ourselves for. I want you to imagine standing in a completely dark room, not dim, dark. Your eyes have not adjusted yet, because there is nothing to adjust to. Then, slowly, Someone turns up a dimmer switch on the wall. The first things you see are the bright shapes, the largest galaxies, the ones close enough or luminous enough to have already been catalogued by other telescopes. They emerge first, like the outlines of furniture in a familiar room. You recognize them. You have seen their kind before. Then the dimmer keeps turning, and behind those bright shapes, a second layer appears. Fainter galaxies, older ones, smaller ones, galaxies that Hubble might have glimpsed as smudges but never resolved. Now Webb pulls them into focus. Spirals with structure, ellipticals with texture, interacting pairs caught in the middle of some slow-motion collision that started before our planet existed. The dimmer keeps turning. A third layer appears, galaxies from further back still, from the era when the universe was only 1 billion years old, then 500 million, then 300 million. Compact, red, strangely bright for how young they are. Galaxies that early theories said should not even exist yet in that quantity, at that size, at that brightness. And yet, there they are, layered behind the ones we already knew about. The dimmer keeps turning, and a fourth layer appears. This is the layer nobody expected. This is the one that changes things. At first, the researchers looking at these images assumed the faintest specks were noise. Every telescope has noise. Cosmic rays hitting the detector, thermal fluctuations, random photons doing random things. When you push a sensor to the edge of what it can perceive, some of what you see is just the sensor talking to itself. So the tiniest, dimmest specks in the deepest Webb fields were initially set aside, catalogued as probable artifacts. Probably nothing. Then the team ran the data again and again. They stacked exposures. They cross-checked wavelengths. They looked for the telltale signatures that separate a real distant galaxy from a random flicker of noise. And one by one, those tiny specks began to resolve. They had the spectra of galaxies. They had the redshifts of galaxies. They had the shapes, however blurred, of galaxies. They were not noise. They were real. They were just so faint, so small, so ancient, that no instrument built before Webb could have registered them at all. A whole population of galaxies, hiding beneath the population we already knew. Sit with that for a moment. For decades, we thought we were looking at the full inventory of the observable universe. First 100 billion, then 2 trillion, then, we assumed, some final polish on the number, some slight upward or downward correction, and we would be done. Instead, Webb turned toward a corner of the dark and revealed a layer of galaxies underneath the layer we already had. Not brighter ones we missed, fainter ones we could never reach, smaller ones, older ones, ones so dim that if you gathered all the light from one of them for a full year, it would still be less than what a single candle in your kitchen puts out in a minute. And these are not rare. They are everywhere. Every deep field we point Webb at shows them. Every patch of sky that used to look mostly full now looks even fuller. The count is going up. The layer beneath the layer is real, and it is populated. Here is what nobody told you when the number was 2 trillion. That estimate assumed a certain flaw. It assumed that below a certain brightness, galaxies stopped existing. or existed in numbers small enough to ignore. Webb is telling us that assumption was wrong. There is no floor. There is another basement beneath the basement, and possibly another one beneath that, which means the real number of galaxies in the observable universe might not be 2 trillion. It might be more, meaningfully more, perhaps very much more. And that is where the open loop begins. Because if the count is wrong, then everything downstream of the count is wrong too. Every galaxy is a factory of stars. Every star is a small furnace that will one day burn out. Every burnout leaves behind a remnant. Every remnant, given long enough time, either dissolves or drifts toward one of the enormous black holes that sit patiently at the centers of galaxies, waiting. And every one of those black holes, given long enough time again, will slowly, quietly, over spans of years so long they hurt to imagine, evaporate into nothing. That entire timeline, the whole slow story of how the universe ends, was built on top of a specific count of how many stars have ever burned, on how many galaxies exist, on how much matter is arranged in structures right now, tonight. If Webb has just found a layer of galaxies beneath the layer we already knew about, then there are more stars than we thought, more remnants than we thought, more black holes than we thought, more light in the past, more dark in the future, a longer, denser, richer story than the one we had been quietly telling ourselves. Tonight we are going to trace that story from where we stand all the way forward, through the final generations of stars, through the slow dimming of the galaxies, through the era when nothing is left but the cooling corpses of suns, through the long twilight when even those corpses come apart, through the empire of black holes, which lasts so long that all of previous cosmic history looks like a single spark by comparison, and through the final dark when nothing at all is left except a thin drizzle of particles drifting through a vacuum that keeps stretching, keeps cooling, keeps emptying forever. I want you to hold on to one image before we go there. Somewhere in one of those deep field exposures, there is a single distant galaxy that Webb pulled out of the dark for the first time in the entire history of anyone looking up. A galaxy that no human eye had ever registered before. A galaxy whose light left it more than 13 billion years ago, when the universe was still an infant, and traveled quietly through the expanding dark for longer than our sun has existed, longer than our planet has existed, longer than the atoms in your body have been arranged in the particular pattern they are arranged in now. It traveled through nothing and nothing and nothing, and then, at the exact right moment, in the exact right direction, it landed on a mirror made of gold, floating 1,000,000 miles from a small blue world, and it left a mark. That galaxy is real. It is out there tonight, still burning, though the light we are seeing from it is from a time long before any of that word means what it means. It has a shape, it has stars. It has, almost certainly, planets circling those stars, most of which will never be seen by anyone. I want you to hold that galaxy in your mind, that single, faint, distant, burning thing. We will come back to it at the end of this story. When we do, it will mean something different than it means now. For now, just know that it exists, that it was hidden, that Webb found it, and that there are countless others just like it, layer beneath layer, waiting quietly in the dark for us to look their way. Because once you understand what that layer means, You cannot help but look forward, all the way forward, to where this is going. If the count is wrong, then the fires are wrong too. That is what I keep coming back to. Because a galaxy is not really a thing, not the way a chair is a thing, or a rock, or a planet. A galaxy is a slow verb. A galaxy is fire, arranged. It is the sum of every star inside it, and every star inside it is a small, controlled explosion that has been going on for millions or billions of years. And every explosion is burning through a fixed supply of fuel that will one day run out. That is what a galaxy actually is, at the physical level. A slow furnace, made of many smaller furnaces, each one counting down. So when Webb pulls another layer of galaxies out of the dark, it is not just adding pins to a map, it is adding fires. It is telling us that the universe has been burning brighter and longer and in more places than we thought. That the total number of stars that have ever lived is not 100 sextillion, the estimate we used to work with. It is more, meaningfully more, perhaps a great deal more. And here is the strange, quiet thing about stars. They are the clocks of the cosmos. Every one of them is a stopwatch. Every one of them started ticking the moment it ignited, and every one of them will stop ticking when its fuel runs out. Some clocks run fast. Some clocks run so slowly that they will still be ticking long after everything else has gone quiet. Tonight I want to walk you through those clocks, not quickly, slowly, because once you understand how stars are born, how they burn, and how they die, you understand why the timeline of the universe has the exact shape it does, and you understand why the layer Webb just found underneath the layer we already knew about matters so much. Let us start where every star starts, in the cold, somewhere in the arms of a spiral galaxy, or in the quiet outskirts of an elliptical one. There is a region of space that is not truly empty. It is thin, thinner than any vacuum a human laboratory can produce, but it is not nothing. It is a cloud, mostly hydrogen, a little helium, a trace of heavier elements left behind by generations of earlier stars that have already lived and died. Astronomers call these clouds molecular clouds, because inside them, the hydrogen atoms are cold enough and slow enough to bond into pairs, into molecules, drifting quietly in the dark. These clouds are enormous. Some of them span hundreds of light years. Some of them contain enough mass to make 100,000 suns. And they are cold, truly cold, just a few degrees above absolute zero. If you were to somehow stand inside one, you would not see it as a cloud. You would see it as darkness. It would be so thin, so diffuse, that your hand held in front of your face would look no different than your hand held in front of your face on Earth on a normal night. And yet, over the timescales that stars actually live by, this dark, thin, cold cloud is where everything begins. Something disturbs it. A nearby supernova sending a shock wave across the region. A collision with another cloud. The gentle press of a passing spiral arm. Whatever the trigger, one small pocket inside the cloud starts to compress. And once compression begins, gravity takes over. Gravity is patient. Gravity is the most patient force in the universe. It does not need speed. It only needs time. And time, on cosmic scales, is something the universe has in almost unlimited supply. So the pocket of cold gas begins to pull inward on itself, slowly at first, then faster still. As it contracts, it heats up, the way a bicycle pump heats up when you squeeze air into it. The center of the pocket becomes denser, hotter, until the temperature crosses a threshold that has stayed exactly the same for the entire history of the universe. 10 million degrees. That is the ignition temperature of hydrogen fusion. Below it, hydrogen atoms bounce off each other. Above it, they crash into each other hard enough to fuse. 2 hydrogen nuclei become 1 helium nucleus, and in the process, a tiny sliver of mass is converted into a small, very stubborn amount of energy. That energy pushes outward, resisting the inward pull of gravity, and in the exact moment when the outward push balances the inward pull, a star is born. Not with a bang, with a quiet equilibrium, a balance point that will hold for millions or billions or trillions of years, depending on the size of the star. This balance point has a name. Astronomers call it the main sequence. It is the long, stable middle age of a star, the period when it burns hydrogen at its core, slowly and steadily, without any drama, without any change in appearance from the outside. Most of the stars you can see in the sky tonight are in this phase. Our own sun is in this phase. It has been in this phase for about 4.5 billion years, and it will remain in this phase for about another 5 billion. But here is where the paths begin to diverge, because the size of the star determines everything about what happens next. Consider the massive ones first, the blue giants, the stars 20 times, 40 times, sometimes 100 times the mass of our sun. These stars are the celebrities of the cosmos, bright, hot, glorious, and doomed. Their sheer weight forces their cores to burn hydrogen at rates so extreme that they run through their fuel in only a few million years. Not billion, million. A blink on cosmic timescales. Then, when the hydrogen is gone, they begin fusing helium into carbon, then carbon into oxygen, then oxygen into neon, neon into silicon, silicon into iron, each step burning faster than the last, each step producing less energy, until the core is a ball of iron, and iron cannot be fused into anything heavier without absorbing energy rather than releasing it, and that is when the star fails. In an instant, the outward pressure vanishes, gravity wins, the outer layers collapse inward at 1/4 of the speed of light. They hit the iron core, they bounce, and the whole star is torn apart in an explosion so bright that it can, for a few weeks, outshine every other star in its host galaxy combined. That is a supernova, a single stellar clock that ran itself down to 0 in an astronomical afternoon and detonated on the way out. What is left behind depends on how massive the original star was. Sometimes a neutron star, a corpse so dense that a spoonful of it would weigh more than every human being on Earth put together. Sometimes a black hole, an even denser corpse, a place where the star has collapsed so completely that not even light can escape from what used to be its center. Either way, the star is gone. Its clock has stopped. Now consider stars like our sun, middle-sized, yellow, ordinary. These are the stars that live for around 10 billion years. They too burn hydrogen at their cores, quietly, patiently, for for most of their lives. But when the hydrogen runs out, something different happens. Without the pressure of ongoing fusion to hold it up, the core begins to contract. As it contracts, it heats. As it heats, hydrogen in a shell around the core begins to fuse. That new shell of fusion pushes the outer layers of the star outward and outward and outward until the star has swollen to hundreds of times its original size. This is what we call a red giant. When our Sun reaches this phase, in about 5 billion years, it will grow so large that it will engulf Mercury and Venus, and it will scorch Earth into a lifeless cinder if the planet is still there at all. Eventually, the red giant sheds its outer layers gently, like a candle blowing away its own smoke. What is left is the exposed core, a small, dense object about the size of Earth, but containing most of the original mass of the star. This is a white dwarf. It does not burn. It has no fuel left. It simply glows with the leftover heat of its former self, and it will glow and cool and glow and cool for a very long time, longer than the current age of the universe. Longer than most numbers you have any intuition for, until eventually, if the universe lets it, it fades into what astronomers call a black dwarf, a cold, dark, invisible corpse. No star has ever finished this process yet. The universe has not been running long enough. Now consider the smallest kind, the red dwarfs. I want you to slow down for this one, because these are the stars that matter most for the end of our story, and they are the ones nobody quite pictures when they think of the sky. A red dwarf is a star with less than about half the mass of our Sun, sometimes much less, as small as 8% of the Sun's mass, which is the physical floor below which fusion cannot ignite at all. They are dim, they are cool. Their surfaces glow at temperatures much lower than our Sun's surface, giving them their characteristic deep orange-red color. If our Sun were replaced by a red dwarf, the sky on Earth would be dim and warm and strange, and most of its light would be pouring out in the infrared, invisible to human eyes. But here is the thing about red dwarfs. They are patient, deeply, profoundly patient. Because they are so small, the pressure and temperature at their cores is much lower than in bigger stars, and the rate at which they fuse hydrogen is much, much slower. They also do something the Sun cannot. They stir. Their interiors are fully convective, meaning the hydrogen in the outer layers is constantly being cycled down into the core. Nothing goes to waste. Every hydrogen atom the star owns will eventually be fed into its furnace. A Sun-sized star only ever burns through about 10% of its total hydrogen. A red dwarf burns through nearly all of it. The result is a lifespan almost too long to hold in your mind. The smallest red dwarfs can burn steadily for tens of trillions of years. Some estimates go higher, 12 trillion, 50 trillion, 100 trillion. Compare that to the age of the universe right now, roughly 14 billion years, and you begin to see the shape of the problem. Not a single red dwarf that has ever formed in the history of the cosmos has aged noticeably yet. Not one. Every red dwarf that ignited when the universe was young is still, essentially, a newborn. Their clocks tick so slowly that 14 billion years is barely a heartbeat to them. I want you to sit next to one of these stars for a moment. Not literally, imaginatively. Picture yourself standing on a small rocky world orbiting a red dwarf somewhere in a quiet corner of a distant galaxy. The star hangs in the sky, a deep orange disk, larger looking than our sun because you are closer to it, but so much dimmer that the light around you feels like a permanent late afternoon. There is no glare. The shadows are long and warm. The wind, if there is any, is soft. And the star does not change. Not that day, not that year, not that 1,000 years, not that 1,000,000 years. You could stand there for the entire history of our sun, from ignition to future engulfment of Earth, and the red dwarf beside you would look identical at the beginning and at the end. 1,000,000,000,000 years would pass for it, like a single quiet afternoon passes for you. That is the pace of the smallest stars. That is why they matter, because when the sun-sized stars have all burned out and the blue giants exploded long before that, the red dwarfs will still be there, still glowing, still stirring, still slowly, patiently, burning through the last of their fuel. They are the last generation, the final holdouts, the stars that will keep the sky lit, however faintly, long after every other kind of star has gone dark. Which brings us to the second part of this, because it is not enough to know how long stars live. You have to know when they are being made. And here the story starts to bend in a way that surprises people. If you were to graph the star formation rate of the universe against cosmic time, you would not get a rising curve, or a flat one, or a curve that keeps climbing. You would get something that looks like a hill. It starts low, near the very beginning, in the era just after the first galaxies began pulling themselves together out of the dark. It climbs steeply through the first 1,000,000,000 years or so, as more and more cold gas collapses into more and more stars. It reaches a peak somewhere around 3 to 4 billion years after the Big Bang, an era astronomers sometimes call cosmic noon. And then, from that peak, it falls, not steeply, gently, but continuously. And it has been falling for the entire time since. We are on the downslope. Right now, tonight, as you listen to this, the universe is still making stars. Yes, our own Milky Way still forms a few new suns every year. Every galaxy Webb has ever photographed still has star-forming regions somewhere inside it, but the total rate across the whole cosmos is a fraction of what it was at cosmic noon, perhaps a tenth, perhaps less. The great age of stellar birth is behind us. Here is the scale translation, so it lands properly. Imagine the entire history of the universe as a single night, not 14 billion years long, just one long night, 12 hours from dusk to dawn. On that scale, the first stars ignited within the first minutes of dusk. The peak of star formation, cosmic noon, would fall a little before midnight. And right now, tonight, in this moment, the universe is somewhere just past 2 in the morning. The lights are still on, the party is still going, but the momentum has clearly shifted. The music is quieter, fewer new arrivals. Most of the guests who are ever going to show up have already shown up. What remains is the long, slow winding down of a party that had its brightest hour hours ago. Or picture a candle, not a small one, an enormous one, the kind that could burn for weeks. When the universe was young, that candle was fresh, waxy, full. New stars were being formed at a rate we cannot easily imagine today. Then the flame ate steadily downward, and the wax pooled and dripped, and now, if you were to look at the candle tonight, you would see that most of the wax is already gone. The flame is still there. It still lights the room, but it is burning down toward the base of what remains. Every year that passes, the candle is a little shorter than the year before. And here is where the second open loop of tonight's story begins. Star formation in this universe will not slow down forever and asymptote to some tiny non-zero rate that keeps going indefinitely. It will stop, not fade, not diminish, stop. There is a moment far ahead of us on the timeline when the last star that will ever form in the observable universe will ignite for the first time. After that moment, no new stars will ever appear. Every star that will ever exist will already exist. The great furnace of stellar birth will simply run out of fuel. I am going to name that moment later in this story. I am going to tell you when it is. I am going to walk you through what the sky looks like in the era just before it happens, and what it looks like in the era just after. Because when star formation stops, the universe crosses a threshold from which there is no going back. Everything that follows is a kind of long, slow settling, a cooling of what was already burning, a dissolution of what was already built. That threshold has a date, in a sense, and when we reach it in our timeline, I want you to feel the weight of what it means. For now, hold that thought. The great stellar factory will run down, not because the universe is broken, because the universe is finite in the specific ways that matter for star making. There is only so much cold gas. There is only so much hydrogen. There is only so much room in the shrinking budget of raw material. And when the budget is spent, the factory closes. I want to end tonight's part with a small image, a single image, the kind you can carry with you into sleep. There is a galaxy out there right now, tonight, at this exact moment, as the words of this story reach you, that is still glowing beautifully. It has spiral arms threaded with young, hot blue stars. It has quiet outer regions where red dwarfs sit patiently in their long afternoon. It has clouds of gas and dust that are still, slowly, giving birth to new suns. From a distance, it looks like a galaxy in the fullness of its life, whole, bright, alive, full of promise. But the truth is that its brightest days are already behind it. It does not know that, in whatever sense a galaxy could be said to know anything. The stars inside it do not know that. The planets orbiting those stars, if there are any, and there almost certainly are, do not know that. From the inside, everything looks fine. Everything looks full. Everything looks like it will keep going, as it has always kept going. And it will keep going. For a very long time, trillions of years. In some places, longer still, in others. But the peak has passed. The candle is burning downward. The party is past midnight. And somewhere out ahead of every galaxy in the observable universe, including the one glowing quietly in that distant patch of sky, there is a final star, a last ignition, a closing of the door on the entire era of stellar birth. Sleep on that, gently, for tonight. We are going to meet that door in the next part. 100 trillion years. Say it slowly. 100 trillion in the shorthand of physicists, 10 to the 14th power years. A 1 followed by 14 zeros. That is the number I want you to sit with for a moment, because it is the number where the door closes on the era of stars. Let me put it inside a frame you can hold. The universe right now is around 14 billion years old. 14 billion. That is the total age of everything you have ever heard of. Every galaxy. Every atom in your body. Every photon that has ever traveled across space. Every idea any conscious being has ever had. Anywhere. On any world. All of it fits inside 14 billion years. Now, imagine a lifespan 7,000 times longer than that. Not 7 times, not 70 times, 7,000 times. Take everything that has ever happened, from the first heartbeat of the universe to this exact quiet moment where you are listening to these words, and repeat it 7,000 times back to back, and only then do you arrive at the moment we are about to describe. That is where the era of star formation ends, not slows down, ends. And here is the strange, unsettling part. That moment, 7,000 cosmic ages from now, is only the first chapter of the ending. The universe does not stop there. It keeps going. It keeps darkening. It keeps thinning. Everything that follows 100 trillion years is much longer than everything that came before. We are, in a very real sense, still in the opening pages of the story. Tonight, we are turning to the page where the first chapter closes. I want to walk you into that era slowly. I want you to feel what it looks like, not just what it means. Picture the sky above a hypothetical planet during the final generations of stars, not our sky. Not the crowded, sparkling blanket you might have seen if you have ever stood outside in a dark place on Earth. That sky belongs to now, to the young universe, to the era of abundance. The sky in the final generations is a different kind of sky. There are fewer stars. That is the first thing you notice. Where our own sky holds thousands of visible points of light on a clear night, this sky holds a handful, and every one of them is red. Not the pale yellow of our sun, not the sharp white blue of a hot young giant. Deep, dim, patient red. The colour of banked coals in a fireplace at the end of a long evening. That is what the sky looks like at the end. There is also more distance. The universe has been expanding the whole time, quietly, in the background, since the beginning. Space itself has kept stretching. Galaxies that once sat close enough to see clearly have drifted apart. By this point, most other galaxies have receded so far that their light is no longer detectable at all. Whatever galaxy your imaginary planet lives inside, that galaxy is essentially alone in the dark. There is no wider community of light out there. There is no larger cosmos you can look up and see. Just your galaxy, or what remains of it, and beyond it, an expanding emptiness that contains nothing you can perceive. Inside the galaxy itself, the population has thinned. The bright blue giants died first, tens of millions of years after the young universe first got going, in a series of brilliant supernovae that seeded the cosmos with heavier elements and then went quiet. The sun-sized stars followed next, one by one, over billions of years, each swelling into a red giant and then softly shedding its outer layers and settling into a small, dim white dwarf. That process kept going and going, generation after generation, star after star, until every yellow star that had ever ignited was gone, turned off, reduced to its cooling core. By the time we reach 100 trillion years, only the smallest stars are still burning. The red dwarfs, the patient ones from the last chapter, the ones that were newborns when the universe was 14 billion years old and are only just now, after 7,000 more cosmic ages, beginning to run out of fuel. They hold on longer than anything else. Every single one of them, because they burn so slowly, because they stir their own hydrogen so patiently, because they are so small that their cores never demanded much energy in the first place. They were the last to ignite, and they are the last to die. In this era, they are the entire sky. But even the red dwarfs cannot go forever. Their hydrogen is finite. Every gram of it will eventually be fused into helium, and once the star is nothing but helium at its core, the fusion slows, then falters, then stops. The star begins to shrink. It does not swell into a red giant the way the sun would. Red dwarfs are too small for that. They simply contract. Their surfaces get bluer briefly, then dimmer, then dimmer, then dark. And then, one by one, over the closing stretch of the stelliferous era, the red dwarfs go out, not all at once, not dramatically, just gradually, over a very long stretch of time. The sky above every hypothetical planet gets emptier and quieter. 500 stars, then 100, then 20, then 5, then 1, then, eventually, none. That is when the door closes. The moment when the last red dwarf finishes its fuel and cools into a corpse is the moment star formation as an era in the universe is over. Not because there was some cosmic decision, because there is no more raw material to make new stars from. The cold hydrogen that once filled the space between suns has been converted into stars, then blown out into supernova wind, then diluted by the ongoing expansion of space, until the remaining supply is too thin and too diffuse to ever collapse into anything new. There is not enough gas left in any one place. There is not enough gravity in any one region. The stellar factory has closed. That is the moment. That is what I promised you I would name. I want you to sit with it for a second, because from that moment onward, no new stars will ever form in the observable universe. Not one. Not somewhere far away that you cannot see. Not in some distant galaxy that has managed to hold onto a little more gas everywhere, simultaneously. The great furnace of stellar birth is done. The candle we described in the previous part has burned all the way down to the base. There is no more wax. There is no more flame. There is only smoke, cooling into a still room. And here is where we cross into what astronomers call the degenerate era. The word degenerate here is not a moral word. It is a physical word. It describes matter that has cooled to a state where all of its electrons are packed as tightly as the laws of quantum mechanics will allow, filling every available energy level from the bottom up. Matter in this state does not burn. It does not fuse. It does not evolve in the way that living stars evolve. It just sits. It cools. It waits. The degenerate era is the era of stellar remnants. It is a universe where the sky is populated not by stars, but by the corpses of stars. Every point of light you might have seen at cosmic noon is now a small dark object drifting quietly in the dark. And there are three main kinds of these corpses. I want to walk you through them, one at a time, so you can picture the population. The first are the white dwarfs. These are the leftover cores of sun-sized stars. When a yellow star like our Sun finishes its life, it sheds its outer layers gently and leaves behind a dense core about the size of Earth, but containing most of the original mass of the star. That core is a white dwarf. It glows with the residual heat of what it used to be, and it cools over unimaginable stretches of time. In our current universe, no white dwarf has finished cooling yet, because the universe has not been running long enough. In the degenerate era, they have had all the time they need. They cool and cool and cool, and they fade from white to yellow to orange to red to invisible. Once a white dwarf drops below a certain temperature, it stops emitting anything a human eye could ever register. At that point, we call it a black dwarf, not a black hole. A black dwarf, a cold, dark, invisible corpse that once was a star. The second kind are the neutron stars. These are the corpses of massive stars that were not quite massive enough to become black holes. When such a star exploded as a supernova in the distant past, its core was crushed so tightly that the electrons in its atoms were pressed into the protons, forming a solid ball of neutrons about 20 kilometers across. A single spoonful of neutron star material would weigh more than a mountain. In the young universe, some neutron stars spin rapidly and emit beams of radiation, and we call those pulsars. But over time, they slow down, they cool, they go silent. In the degenerate era, they are simply sitting, dark, cold, undetectable except by the faintest tug of their gravity on anything that happens to pass nearby, and nothing much passes nearby anymore. The third kind are the brown dwarfs. These are the almost stars. Objects that formed from cold hydrogen clouds but never quite reached the mass required to ignite fusion in their cores. They are heavier than the largest gas giant planets, but lighter than the smallest true stars. They glow faintly from the leftover heat of their formation, but they do not burn. They have always been dim, and by the degenerate era, they are almost invisible. Cold, dark, silent objects drifting quietly among the dead stars, adding their tiny contribution to a sky that contains almost nothing. That is the sky of the degenerate era. White dwarfs cooling into black dwarfs, neutron stars sitting silent, brown dwarfs that never quite ignited, softly fading. Every so often, a rare collision, when two remnants happen to drift close enough to each other to merge and produce a brief flash of light. But those are exceptions. The default state of the sky is dark and gets darker every year. I want you to picture a night on a hypothetical planet during this era. Assume, for the sake of imagination, that the planet still exists and still orbits something. Assume the something is a very cold white dwarf, glowing faintly, providing the barest amount of warmth. You step outside. You look up. There is no Milky Way overhead. There is no band of stars stretching from horizon to horizon. There is no scatter of bright points across the sky. There is, at most, a handful of extremely faint dim red spots, so dim you have to look at them out of the corner of your eye to see them at all. And beyond those, there is nothing. not blackness containing hidden distant galaxies, real nothing. The universe has expanded so much by this era that there is no other galaxy left within observable range. Everything else has drifted beyond the horizon of visibility. Your galaxy, whatever remains of it, is alone in an empty universe. Your sky is the sky. It is very quiet. Now, I have to be honest with you about what this feels like when you describe it. It sounds like tragedy. The word that keeps trying to arrive when you talk about this era is loneliness. And I understand the pull of that word because from a human vantage point, looking at that sky, imagining a planet with no companions, no wider community of light, no distant galaxies to reach toward, it does feel lonely. It feels like a story ending badly. It feels like the universe going hollow. And yet, this is the pivot. This is the thing that keeps me from calling it tragedy. The universe does not feel it. There is no one there to feel it. By the degenerate era, whatever biological life once existed on whatever planets have not already been destroyed will be long, long gone. Complex life requires warmth, and warmth requires stars, and stars are almost all gone by then. There are no observers standing on cold planets looking up at empty skies with sadness. There are no consciousnesses grieving the loss of the Milky Way. The empty sky is not empty for anyone. It is just empty. That is the strange mercy of the timeline. The bleakness we are describing exists only in our imagination. Right now, warm and alive, from the vantage point of cosmic noon, projecting our own capacity for loss onto a future that will not contain anyone to bear it. The universe does not mourn its own dimming. The universe is not lonely. Loneliness is a property of minds, and by the time the sky is truly empty, the minds are gone. There is something almost gentle in that. The final chapters of the universe are being written in a language that has no readers. Whatever unfolds after the last consciousness fades is unwitnessed, which means, in a strange and quiet way, it cannot hurt anyone. The dying, if we can call it that, happens in a completely dark room where no one is left to notice. I keep coming back to that thought. It does not make the timeline any less real. It does not make the physics any less inevitable, but it does soften something. The dread we feel when we imagine an empty sky is our dread projected forward. It is not the universe's dread. The universe has no dread. It just has slow, steady, patient physics unfolding across timescales that dwarf every human category. And now, I want to bring you back to something we started this whole story with, because we are not quite done with part 3, and I do not want you to lose the thread. Remember the layer that Webb pulled out of the dark, that deep, deep field, that patch of sky where the bright galaxies came first, then the fainter ones behind them, then the fainter still, and then the ones beneath even those. Remember the tiny specks the researchers first thought might be noise, and then realized were galaxies. Small ones, ancient ones, faint ones, ones so dim that the light of a full year from one of them would still be less than a candle in your kitchen for a minute. Every single one of those specks is a galaxy that will pass through the era we just walked you into. Every one. That faint smudge on the edge of Webb's detector, the one nobody would have noticed before this decade, the one that exists only because of a golden mirror floating 1,000,000 miles from Earth. That galaxy will one day watch its brightest stars die in spectacular supernovae. Then its sun-sized stars will one by one swell into red giants and settle into cooling white dwarfs. Then its red dwarfs will hold on for trillions of years, glowing dim and patient. Then, at last, its final red dwarf will burn out, and its sky, wherever there was ever any observer to have seen a sky, will empty, just like all the others. The layer beneath the layer that Webb just discovered is not a layer of exceptions, it is a layer of participants. Every galaxy in that deep field, every faint smudge, every one of those ancient tiny points of light is walking the same road. Some of them started earlier than we thought. Some of them are older than we thought. Some of them have already burned through more of their stellar budget than we would have guessed. But every one of them is heading toward the same destination. The end of star formation, the transition into the degenerate era, the slow cooling of the corpses. That is the shape of the timeline. It is not one galaxy dying while the rest thrive. It is not one region going dark while other regions stay bright. It is a universal process playing out in every galaxy Webb has ever photographed, and in every galaxy Webb will ever photograph, and in every galaxy that no telescope will ever see because its light will never reach us. All of them, all the way down, layer beneath layer beneath layer. Sit with that for a moment before you close your eyes tonight. Not with dread. There is nothing to dread. The universe does not dread. Just with the quiet recognition that what we are describing is what actually happens. And it happens everywhere, and it happens patiently, and it happens without anyone watching. That patch of sky Webb photographed contains thousands of galaxies. Some of them are burning brightly right now in whatever moment their local now happens to be. Some of them are on the downslope from cosmic noon, like ours. Some of them have already started thinning. All of them will, in the fullness of time, arrive at the empty sky we just described. The layer beneath the layer is not just a discovery about how many galaxies exist. It is a discovery about how many participants there are in the long, slow dimming to come. And the dimming, as long as it feels, is only the first chapter. The next chapter is longer, much stranger, and it is where we are going next. We have talked about the deaths of stars. Now I need to tell you about the death of galaxies themselves. Because here is something that most people never quite realize when they look at a picture of a spiral or an elliptical or a distant smudge in a deep field. A galaxy is not a fixed object. A galaxy is not a permanent arrangement. A galaxy is a temporary pattern held together by gravity. And gravity, given long enough time, does not just hold, it rearranges, it sorts, it empties, it undoes. Every galaxy you have ever seen in an image, every one of the ones Webb pulled out of the dark last year, every one of the ones in that new layer beneath the layer we already knew about, is coming apart, slowly, gently. Over timescales so long that the entire lifespan of a star looks fast by comparison, but coming apart nonetheless. I want to walk you through how that happens. Not because it is frightening. It is not frightening. It is just what gravity does when you leave it alone for a very long time. Think about what a galaxy actually is. At the level of its bones. It is a collection of stars, all in orbit around a common center of mass. Some of them close to the center, some of them far out in the halo. Each one is on its own path, moving through the shared gravitational field of the whole galaxy. From the outside, over a human lifespan, everything looks fixed. The Milky Way in a photograph tonight looks essentially identical to the Milky Way in a photograph 100 years from now, because 100 years is nothing on the timescale of galactic motion. Even 1,000,000 years is barely a flicker. Our Sun, orbiting the center of the Milky Way, takes about 230 million years to complete just one lap around the galactic core. A galaxy is a place where the clock ticks in units we can barely feel. But if you let the clock keep ticking, past the era of star formation, past the death of the last red dwarf, past the moment when every remaining star has cooled into a corpse, into timescales measured in quadrillions and quintillions of years, something starts to happen to the orbits themselves. Stars in a galaxy do not stay put, not because anything drives them away, because they interact with each other gently over vast stretches of time, and every interaction shuffles the deck a little. Two stars pass close to each other, not close enough to collide, just close enough that their gravity tugs on each other, briefly, in a kind of slow gravitational handshake. One star ends up moving a little faster. The other ends up moving a little slower. The energy has been redistributed. Nothing dramatic, just a whisper of exchange. Now imagine that whisper happening billions of times, all across a galaxy, over trillions upon trillions of years. Every star, every stellar remnant, every cold white dwarf, every silent neutron star, participating in a slow, endless dance of near misses and near passes and gravitational handshakes. Astronomers have a name for this process. They call it two-body relaxation. It sounds gentle, and it is gentle, in the sense that no single interaction is violent. But the cumulative effect, over long enough time, is the complete rearrangement of the galaxy from the inside. Here is what that rearrangement produces. Some stars, through countless lucky interactions, gain more and more energy over time. Their orbits get wider, 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 until eventually one interaction gives them just enough of a kick that they exceed the escape velocity of the galaxy entirely, and they leave. They drift outward and outward and outward, and they never come back. They become intergalactic wanderers, cold, dead corpses of stars, spinning slowly in the empty spaces between what used to be galaxies, alone, utterly alone, nothing near them for distances so vast that even their own gravity has nothing to pull on. Picture that for a moment. A single cold white dwarf, formerly the core of some sun-sized star that once burned in a spiral arm somewhere, now drifting through empty intergalactic space, with no other object within any distance that has meaning. The nearest neighbor is unimaginably far. The nearest anything is unimaginably far. It just drifts and cools and drifts. That is one fate, the escape fate. The other stars, the ones on the losing side of all those gravitational handshakes, do the opposite. They give up energy over time. Their orbits shrink, shrink, shrink. They spiral inward, closer and closer to the galactic center. And at the galactic center, in almost every large galaxy in the universe, there is something waiting. There is a supermassive black hole. In our own Milky Way, that black hole has a name, Sagittarius A star. It is about 4 million times the mass of our Sun, sitting quietly at the center of everything, holding the whole rotating galaxy together like the axle at the center of a wheel. In larger galaxies, the central black hole can be 100 million, a billion, sometimes tens of billions of times the mass of the Sun. Every galaxy that Webb has ever photographed at high enough resolution, every one of them seems to have one of these central engines. They are common, they are patient, and they have been waiting. As stellar remnants slowly spiral inward through the eras of the degenerate universe, they eventually reach the central black hole and are absorbed. Not violently, not with a flash, just absorbed. And the black hole grows. A tiny bit at a time. One cold white dwarf, one silent neutron star, one drifting brown dwarf that never quite ignited. Over spans of time so long that words like eons and epochs feel embarrassingly small, the central black hole feeds on the slow rain of remnants falling toward it, and it grows heavier and heavier and heavier. This is happening in every galaxy simultaneously, everywhere, in every one of those faint smudges Webb found in the deep field, in every one of the layer beneath the layer. Some stars are being flung outward into permanent exile in intergalactic space. Others are being drawn inward and swallowed by the central black hole. The galaxy is being sorted, one particle at a time, into the two categories that gravity ultimately allows: escapee or captured. By the time this sorting process has fully run its course, over spans of roughly 10 to the 20th power years, or 100 quintillion years, the galaxy no longer exists as a galaxy. The structure has dissolved. What used to be a spiral, or an elliptical, or an irregular, or any of the beautiful shapes we photograph today, has come apart. All that is left is a single supermassive black hole, much larger than it was at the beginning of the process, sitting alone in a region of space that used to hold 100 billion stars. Everything else has either been eaten by the black hole or has drifted away into permanent solitude. Let that image sit for a moment. Every galaxy you have ever seen, every spiral in every textbook, every elliptical in every documentary, every faint smudge in Webb's deepest field, every single one, in the fullness of time, comes down to a lone black hole and a scattering of cold escapees drifting outward through an expanding dark. That is the end state of galaxies. That is what gravity produces when you leave it alone long enough. I want you to feel the strangeness of this, because we tend to think of galaxies as the fundamental units of the cosmos. They are the biggest things with names. They are the structures that scale up from stars and scale down from the cosmic web, and we think of them as durable, ancient, almost eternal. But they are not. On the timescales we are working with tonight, galaxies are as temporary as everything else. They just take longer to fall apart. The very structure that Webb just found more of, layer beneath layer, is temporary. Every one of those tiny faint galaxies from the earliest universe, every one that had never been seen before, every one that surprised us into rewriting our count, is on the same long journey toward dissolution. The count is bigger than we thought. The story is the same. Now, there is one more thing I need to tell you about this era. It is a possibility, not a certainty, and I want to be careful about that. But it changes the timeline in a way you should know about. Matter itself may have a shelf life. Here is what I mean. The building blocks of everything you know, everything you have ever touched, every atom in your body, every atom in every planet, every atom in every star and every stellar corpse, are built out of a small number of subatomic particles, electrons, neutrons, and protons. Protons are what sit at the heart of every atom. They are what makes hydrogen, hydrogen, and carbon, carbon, and iron, iron. They are the deepest layer of ordinary matter. For a long time, physicists believed protons were stable, completely stable, truly forever objects. But some of our best theories about how the fundamental forces of nature are unified suggest that protons might, at some incredibly slow rate, be capable of decaying, falling apart, breaking down into lighter particles and eventually into radiation, not on any timescale we could ever measure in a lab. Experiments have shown that if protons do decay, the average lifetime of any individual proton must be at least 10 to the 34th power years. Let me say that again. 10 to the 34th power years. A 1 followed by 34 zeros. That is roughly a trillion times the current age of the universe. We have not yet observed a single proton decaying, ever, in any experiment. What we have done is watched enormous tanks of water containing trillions of protons for years at a time, and confirmed that whatever the decay rate is, it must be slower than that lower limit, which means either protons never decay at all, and matter is truly permanent, or they do decay, but so slowly that we cannot yet catch one in the act. Suppose they do decay. Suppose the theories that predict this turn out to be right. Then the story of the universe gets a new chapter that I have to describe carefully, because it is almost too vast to hold. Every cold white dwarf drifting alone in intergalactic space would slowly, atom by atom, lose its protons. Not fast, absurdly slowly, but over enough time, every proton in the object would eventually decay into lighter particles and radiation. The white dwarf would evaporate, not through heat, not through gravity, just through the slow, patient decay of its own building blocks. The same would be true of every neutron star sitting silent in the intergalactic dark. The same would be true of every planet that has somehow survived being swallowed or ejected. Anything made of ordinary matter would, over spans of 10 to the 40th power years or longer, quietly turn itself into radiation and leave nothing solid behind. Every stellar remnant in the universe, gone, not eaten, not destroyed, just gently unmade. Let me try to translate this timescale, because at this point the numbers stop meaning anything unless we put them next to something. Imagine that the entire current age of the universe, all 14 billion years of it, from the first fraction of a second after the Big Bang to this exact quiet moment, was a single grain of sand. Then the era of star formation would be a small handful of grains. The era in which the last red dwarf finally burns out, 100 trillion years from now, would be a small bowl of sand. The era in which galaxies fully dissolve through gravitational relaxation, 100 quintillion years from now, would be a large bucket of sand. And the era in which protons finish decaying, if they decay at all, would be an entire desert, miles across, horizon to horizon, uncountable grains of sand, and each one is another entire current age of the universe. That is the scale we are working with. Every previous era we have described, from the Big Bang to the dissolution of galaxies, is a tiny corner of a much, much longer story. The universe, if protons decay, has room for eras that make everything up to now look brief. And here is where I want to widen the lens a little, because there is a thought I keep coming back to, and I want to share it with you gently, in case it sits with you the way it sits with me. Look at what we have described tonight. Atoms are temporary. If protons decay, the atoms in your body will one day cease to exist as atoms. Stars are temporary. Every one of them is a countdown, and the countdown always ends. Galaxies are temporary. Even the biggest, brightest, most permanent-looking galaxies in the deepest fields Webb has ever photographed come apart in the end. And the cosmic web itself, the vast filaments of galaxies and clusters that shape the largest visible structures in the universe, is temporary too. Every filament, every cluster, every wall is made of the same galaxies that will eventually dissolve. When they dissolve, so does the web. So does everything above the web. Nothing on any scale, from the subatomic to the cosmic, is exempt. That is a strange thing to sit with. We are so used to permanence. We build our lives around the assumption that certain things stay, that mountains stay, that oceans stay, that the sun stays, that the stars stay. And on the timescales of a human life, they do stay. All of them stay. The sun today looks essentially identical to the sun the day you were born. The constellations today are essentially identical to the constellations that our ancestors named thousands of years ago. Permanence at the human scale is the default. It is what everything looks like. But it is not what everything is. It is only what everything looks like from our vantage point, standing this close to the timeline in this brief window of cosmic history. Zoom out far enough and permanence dissolves. Everything is passing through. Every atom, every star, every galaxy, every filament of the cosmic web. All of it, on its own timescale, is in motion. All of it is unraveling. All of it is a temporary arrangement that gravity and entropy, and possibly the slow decay of matter itself, are quietly undoing. The deep field that Webb just took, the one with layer beneath layer beneath layer, is a snapshot. That is the right word for it. A snapshot. It captured what those galaxies looked like at a specific instant, in a specific arrangement, in the specific era of the universe, when their light happened to be traveling past our small planet. If we could somehow revisit that same patch of sky 10 to the 20th power years from now, none of what we photographed would be there. The galaxies would be gone. The stars in them would be gone. The structures would be dissolved. What we would see, if we could see anything at all, would be a scattering of quietly growing black holes in a much emptier region of space. I want to end tonight's part with that image, because I think it is important to hold it clearly, even though it is a difficult one to hold. Take one of the galaxies from the deep field. Pick any one. Pick the faintest one you can imagine. Pick the one Webb barely resolved from noise. It is a real galaxy. It exists tonight. It has stars burning inside it right now, in whatever local moment its own physics considers now to be. It has structure. It has motion. It has some form of activity somewhere in its interior. It is alive. In the loose way, we might apply that word to something that burns. Now advance the clock, trillions of years, hundreds of trillions, quintillions, longer. Eventually, The region of space where that galaxy once was contains only one thing: a single supermassive black hole, slowly growing on the last stellar remnants that spiraled inward toward it. Around it, in the volume of space that once held the galaxy, there is essentially nothing. A drift of neutrinos, ghostly particles from ancient supernovae and from the very early universe, moving through the emptiness at almost the speed of light, interacting with almost nothing. A whisper of leftover photons stretched out by the ongoing expansion of space into wavelengths so long they are barely detectable, and the black hole itself at the center, silent, patient, dark. That is what remains of the galaxy. A black hole and a thin drift of neutrinos, and the last cold photons of a light that finished shining long ago. Every faint smudge in that deep field ends up like this. Every one. The bright ones and the dim ones. The ones we always knew about and the ones Webb just found beneath the layer we already knew. All of them dissolving into the same silent state. But the black hole itself, the one at the center of what used to be the galaxy, is not the end. That is the surprising thing. That is what I want you to hold overnight and carry into the next part. Because even the black hole is not permanent. Even it has a countdown. And in the next chapter of this story, we are going to watch it run. The universe has become an ocean of dark. I want you to picture that carefully. Not a room with the lights off. Not a night on a distant planet where a few red stars still hang in the sky. An ocean, vast beyond meaning, cold beyond intuition, and empty. Empty in a way we have no proper word for, because every empty room you have ever stood in still had walls, and a floor, and a ceiling, and air, and warmth, and the near presence of other things. This ocean has none of those. It has no walls. It has no near presences. It has almost no matter of any kind. It is stretched and stretching still across distances so vast that light itself, moving at 300,000 kilometers per second, cannot cross meaningful portions of it in what remains of eternity. And floating in that dark, scattered at distances so enormous that we lose the ability to describe them, are the final structures the universe has left. The black holes. Some of them are small in the language of black holes, which means a few times the mass of our sun. These are the corpses of massive stars that died long, long ago, back in the era when there were still stars to die. Their surfaces, if we can call the event horizon a surface, are only a few kilometers across. If you could somehow see one, which you cannot, it would look like a small sphere of absolute black, occluding whatever thin trickle of light happened to be behind it. Some are enormous, truly enormous. The former central engines of galaxies that dissolved trillions upon trillions of years ago. These are the supermassive black holes, ranging from millions to billions to occasionally tens of billions of times the mass of the Sun. Over the eras of galactic dissolution we described in the last part, they grew. Every cold white dwarf, every silent neutron star, every stellar remnant that spiraled inward instead of being flung outward, added a small increment to their mass. By the time we arrive at the black hole era, these central black holes are much heavier than they were in the eras when galaxies still existed as galaxies. Some are so massive that the region of space they occupy is larger than the orbit of Neptune. Some are larger still. Between them, distances that beggar description. whole galactic diameters, and then some. A single black hole may sit in a region of space so isolated that its nearest neighbor is unreachable even in principle, because the universe is expanding faster than any signal it could ever send. They are alone. They are cold. They are patient. That is the era we have entered, the black hole era, the longest chapter of the universe by so much that everything we have described up to this point, from the Big Bang through the death of stars through the dissolution of galaxies, is essentially the prologue. I want to walk you into this era slowly, because it deserves reverence. It is where almost all of cosmic time actually lives, and yet it is where almost nothing happens. For most of this era, from the outside, nothing changes. A black hole sits, it waits. There is nothing near it to fall in. There is no gas to accrete. There is no dust. There is not even, in most regions, any starlight left to catch. The universe around each black hole is simply dark and expanding and quiet. From any hypothetical vantage point, if such a vantage point could exist, which it cannot because there is nothing left to observe from, the sky would show nothing at all, not stars, not galaxies, not distant glows, just a black hole, and beyond it, dark. That is the view from every location in the universe during this era. The same view, everywhere, forever, or nearly forever. But something is happening to those black holes. Something so slow, so quiet, so absurdly gentle that we could not detect it in a laboratory, even if we tried for the entire current age of the universe. And yet, over the eras we are working with tonight, it changes everything. Black holes are not truly black. I want to say that carefully, because it took physics a long time to arrive at the idea, and it still feels strange when you hear it. For most of the 20th century, we thought of black holes as absolute. A region of space where gravity was so strong that nothing, not matter, not light, not information of any kind, could ever escape. If it crossed the event horizon, it was gone forever. The name fit. Black. Then in 1974, a physicist named Stephen Hawking, working through the mathematics of quantum fields near the boundaries of black holes, discovered something that broke that picture. Very carefully, using the tools of quantum mechanics applied to curved space-time, he showed that a black hole should, in fact, emit a faint thermal radiation, a whisper of particles, a tiny outward flow of energy coming from just outside the event horizon. The mechanism is subtle, and I do not want to hand-wave through it, but the plain language version is this: empty space is not truly empty. According to quantum mechanics, the vacuum is constantly, gently fluctuating. Pairs of virtual particles pop into existence for extremely brief moments and then annihilate each other back into nothing. This happens everywhere, all the time, in every cubic centimeter of the universe. Normally, we cannot detect it. The pairs cancel too quickly to notice. But near the event horizon of a black hole, something can go wrong with that cancellation. Occasionally, in the intense gravitational gradient at the edge of the horizon, one member of a virtual pair falls across the horizon and gets trapped inside the black hole, while its partner escapes outward into the surrounding space as a real particle. From the outside, it looks as though the black hole has emitted a particle, From the perspective of the accounting books of energy, that particle has to be paid for somewhere, and the only place it can be paid for is the mass of the black hole itself, which means, very slowly, the black hole is losing mass, bleeding it, one virtual pair at a time, into the surrounding dark. This is Hawking radiation. It is real in the sense that it emerges cleanly from every combination of quantum mechanics and general relativity we know how to write down. It has never been directly measured because it is so extraordinarily faint. But essentially no working physicist doubts that it happens, and its consequences for the long-term fate of the universe are total. Black holes leak. They leak so slowly that, for a black hole with the mass of the Sun, the temperature of the radiation coming off it is around 60 billionths of a degree above absolute zero, colder than any refrigerator ever built, colder than the ambient temperature of the cosmic microwave background. In the current universe, black holes are actually gaining mass faster than they are losing it, because they are absorbing more light and gas from their surroundings than they radiate away. But in the black hole era, there is no more infalling matter. There is no more infalling light. Everything is dark, and the only thing happening to any black hole is the slow outward drip of Hawking radiation. Given long enough time, that drip finishes the job. The smaller black holes go first. Because Hawking radiation depends on the surface gravity at the event horizon, and smaller black holes have proportionally higher surface gravity, they radiate at a higher temperature. Not much higher, but higher. And so they lose mass faster than their larger cousins. A stellar mass black hole, one with the mass of a few suns, takes something in the range of 10 to the 67th power years to fully evaporate. That is a 1 followed by 67 zeros. Try to hold that number in your mind for a moment, 10 to the 67th. It is so much larger than the current age of the universe that the current age of the universe is not a meaningful fraction of it. If you tried to write it out, 10 to the 67th years, you would need a page of digits. And that is only the evaporation time for the smallest black holes, the stellar mass ones, the corpses of former stars. For the supermassive black holes, the ones that once sat at the centers of galaxies, the timescale is much longer. Because Hawking radiation depends on surface gravity, and surface gravity for larger black holes is lower, the radiation coming off a supermassive black hole is even fainter than the whisper coming off a stellar mass one. It is so faint that the temperature of the radiation is smaller than any temperature we can meaningfully imagine, and so the evaporation takes correspondingly longer. For the very largest black holes, the ones that grew during the eras of galactic dissolution to masses of 100 billion suns or more, the evaporation time approaches something on the order of 10 to the 100th power years. 10 to the 100th power years. I want you to hear that number spoken aloud, slowly. A 1 followed by 100 zeros. Written out, it looks like a wall of digits. Written out in scientific notation, it fits on a small piece of paper. Written out in intuition, it does not fit anywhere. There is no comparison in your daily life that maps onto that number. There is no comparison in cosmic history that maps onto it. There is no comparison, really, in any category of experience. Let me try to translate it anyway, even though the translation almost breaks. The current age of the universe is around 14 billion years, 10 to the 10th power years roughly. If you compressed all of cosmic history from the Big Bang to right now into a single second of experience, then the era of star formation ending would take, on that scale, about 2 hours. The era of galactic dissolution would take about 300 years. The era in which stellar mass black holes finish evaporating would take, on that same scale, an amount of time larger than any category you know. And the era in which the largest supermassive black holes finish evaporating would take on that scale so much longer than that even the scale itself becomes meaningless. It is not just longer, it is unimaginably longer. If the entire time from the Big Bang to now is 1 second, then the black hole era, the full run of 10 to the 100th power years, is a duration that would take, on that same scale, longer than the current age of the universe repeated back to back, a trillion times. Every era we have described tonight is the prologue. Every era, the Big Bang, the era of star formation, the era of the death of stars, the era of the dissolution of galaxies. All of them, put together, back to back, do not equal a millionth of a millionth of a millionth of the black hole era. This is the era where the universe actually lives, in terms of pure duration. This is where almost all of cosmic time is spent, and almost none of it contains any events. Sit with that. For most of the black hole era, from the outside, the universe simply is. There are the black holes, floating alone in their vastnesses. There is the ongoing expansion of space, continuing to push everything further apart. There is the faint thermal whisper of Hawking radiation seeping outward from each event horizon, and there is nothing else, nothing at all. For unimaginable stretches of time, trillions upon trillions upon trillions upon trillions of years, just the quiet, slow bleeding of black holes into the dark around them, and nothing to observe it, and nothing to feel it, and nothing to name it. But something is happening. In slow motion, every black hole is losing mass. Every one of them, everywhere in the universe. Some faster, some slower, depending on their size. And here is the strange, almost paradoxical thing about Hawking radiation. As a black hole loses mass, it does not slow down, it speeds up. A smaller black hole radiates at a higher temperature, which means it loses mass faster, which makes it smaller still, which raises its temperature again, which accelerates the process further. The evaporation is not a steady candle burning down at a constant rate. It is a candle that burns faster and faster as it gets smaller, and near the very end, it does not fade quietly. It does not dim into nothing. Near the very end, it flares. I want you to picture this carefully, because it is one of the most quietly astonishing images in physics. Take one of the supermassive black holes. Pick any of them. Pick the one that used to sit at the center of the galaxy, that used to be at the center of Webb's deep field. It has been evaporating for something like 10 to the 99th power years by this point. For almost that entire duration, from the outside, it has looked almost identical, slightly smaller each eon, slightly warmer each eon, but so slowly that the change is beneath any meaningful notice. From billion year to billion year, it looks the same. Then, over the closing stretch of its life, the process accelerates. Its mass drops faster, its temperature rises faster. Over what remains of its existence, on timescales that are still absurd by any human standard, but a brief compared to the eras of its earlier evaporation, the black hole begins to brighten, not fiercely, but softly. The Hawking radiation coming off it grows warmer and warmer. Its faint dark presence is now emitting a real, if soft, glow. In the enormous emptiness around it, it is the only thing radiating any energy at all. Then, near the very end, the acceleration hits its final phase. The black hole is now radiating at high enough temperature that its emission is genuinely bright, in the sense that it would be visible to any hypothetical observer, though of course there is no observer left. Its remaining mass drops precipitously, its temperature spikes, and in the final fraction of its existence, over what is, on cosmic scales, an incredibly brief window, it releases everything remaining in a burst. A soft brightening, a final flash, and then nothing. Then nothing. I want to say that again, because I want the shape of it to land properly. There is a slow simmer that lasts for essentially the entire age of the black hole era. Then near the end, a soft brightening over eons that are brief by comparison. Then a final flash. Then nothing. Not a black hole with less mass, not a small remnant, not a residue, nothing. The event horizon collapses to a point and vanishes. Whatever mass was left is radiated away as high-energy particles that stream outward into a universe that has no boundary and no observer. The place where the black hole was is now, physically, the same as every other place in the universe around it. Empty, cold, silent, expanding. Every single black hole in the universe ends this way. The small ones first, over what still amounts to unimaginable timescales, then the medium ones, then the large ones, then the supermassive ones. Then the largest of the supermassive ones. Each one, in its own local ending, goes through the same sequence. A long simmer, a soft brightening, a final flash, then nothing. By the time the last black hole in the observable universe has evaporated, we are roughly 10 to the 100th power years past the current moment. That is the end of the black hole era. That is the closing of the longest chapter of the entire cosmic story. Everything that will ever happen with mass and structure and gravity has now happened. There are no more black holes. There are no more stars. There are no more galaxies. There are no more remnants. There is no more matter arranged into any coherent form. I want you to hold the image of that deep field one more time before we close tonight's part. Remember what Webb showed us. Layer beneath layer of galaxies, some ancient, some new, some faint, some fainter still. Thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Every one of them a real, present, glowing thing right now. In the black hole era, none of them exist. Not as galaxies, not as stars, not as any structure we would recognize. Every one of them has passed through the dissolution we described in the last part, and every one has left behind a single central black hole, quietly evaporating, alone in an ever-expanding dark. Toward the end of the black hole era, one by one, each of those black holes will complete its evaporation. Somewhere in the enormous emptiness that used to contain the galaxy that Webb pulled out of the dark last year, one specific black hole will run through its final acceleration. It will brighten softly over spans of time that still exceed all previous cosmic history. then it will flash, and then it will be gone. That last flash for that particular black hole will be, for a brief moment, the only source of light in a truly enormous volume of space. A single fading spark in an otherwise completely silent sky. Nothing near it, nothing to catch its light, nothing to notice it happened, and then the spark is gone too. Every faint smudge Webb has ever photographed. Every layer beneath every layer. Every galaxy in every deep field. And every galaxy that no telescope will ever image. Each one, in its own local ending, becomes a single fading spark in a silent sky, and then not even that. Sit with that for a moment, not with dread. There is no one to dread it, just with the recognition that this is the actual shape of the timeline. This is where everything is heading. Long, quiet, patient, and unwitnessed. There is one more part to this story, because after the last black hole has flashed and vanished, the universe is not truly over. There is still something after, something even quieter, something that lasts longer than everything we have described so far, and yet is somehow gentler than what came before. We will meet it in the next part. There is one force we have not properly named yet, and it is time to name it, because without it, the entire ending we have just walked through does not have to happen. Without it, gravity might have written a very different story. Without it, everything we described, the empty skies and the dissolving galaxies and the long, lonely evaporation of black holes, could have curved back on itself into something else entirely. It is because of this one force that the timeline goes the way it goes. It is the reason the ending is an ending. Its name is dark energy. I want to walk into this carefully, because it is one of the strangest ideas in modern physics, and it is easy to make it sound more mysterious than it needs to be. For most of the 20th century, cosmologists thought there were essentially two possible fates for the universe. In one, there was enough matter in the cosmos that gravity would eventually slow the expansion that started with the Big Bang, then reverse it, and then pull everything back together into a hot, dense point, a kind of mirror image of the beginning. That fate had a name, the Big Crunch. In the other fate, there was not quite enough matter, and the expansion would continue forever, slowing steadily, but never quite stopping, drifting outward toward a very cold, thin future. Everyone assumed the answer was one of those two possibilities. All you had to do was measure how much matter existed and how fast the expansion was slowing, and you would know which future you lived in. Simple in principle, difficult in practice. Astronomers spent decades trying to make that measurement precisely. Then, in the late 1990s, two independent teams of astronomers made the measurement. They used a specific kind of exploding star, a Type 1, a supernova, as a cosmic distance marker. By measuring how bright these supernovae looked at various distances, they could work out how fast the universe was expanding at different points in cosmic history. What they found was so unexpected that both teams initially thought there must be an error somewhere in their data. They rechecked and rechecked and rechecked, and the answer kept coming back the same. The universe is not slowing down. The universe is speeding up. Somewhere around 6 billion years ago, something took over the expansion of the cosmos, and that something is pushing everything apart faster and faster, not by much on any local scale. Locally, gravity still wins. The Earth is not flying away from the Sun. The Sun is not flying away from the galactic center. The Milky Way is not flying apart from Andromeda, our nearest large neighbor. On the small scales, gravity still holds everything the way it always has. But on the largest scales, in the vast reaches between clusters of galaxies, expansion is accelerating, and every year it accelerates a little more. The rate at which distant galaxies are receding from us has been growing steadily for the last 6 billion years, and it is projected to continue growing for as far into the future as our current models can reach. We do not know what dark energy is. Let me say that plainly. It is not a metaphor. It is not a name for something we already understand. It is a label we have placed on a real, measured, ongoing acceleration whose cause is presently unknown. It might be a property of empty space itself, a kind of energy that comes with the vacuum simply for existing. It might be a slight incompleteness in our theory of gravity, showing up only at the largest scales. It might be something else that we have not yet imagined. What we know is that its effect is real, its magnitude is measurable, and its consequences for the long-term future are total, because dark energy is what guarantees the ending we have just described. Without dark energy, the expansion of the universe would eventually have slowed and possibly reversed. Given enough time, gravity might have gathered the cosmos back into itself, and everything we walked through tonight, the black hole era, the dissolution of galaxies, the death of the last star, might never have played out the way we described. There would have been a different ending, hotter and denser, perhaps followed by a different beginning. But dark energy is real. It has been measured across multiple independent lines of evidence. It is not going away. And as long as it continues to behave the way it appears to behave, gravity will lose the long war. The universe will keep expanding. It will keep thinning. It will keep cooling. Every distant galaxy will keep drifting further away, faster and faster, until eventually the light from those galaxies stretches beyond our ability to detect it, and they slip past our horizon forever. Not because they stopped existing, because the space between us and them is stretching faster than the light between us and them can cross it. This has a name. The final state that all of tonight's timeline leads into. The state that begins after the last black hole has flashed and vanished. It is called the dark era. I want to describe it slowly because there is something almost sacred in it, even though nothing sacred is left in it to notice. By the time we arrive at the dark era, the universe is unimaginably vast. The observable region, the amount of space accessible to any hypothetical signal, has expanded so much that ordinary comparisons fail entirely. What remains inside that unimaginable volume is very little. A thin drift of photons, stretched to such long wavelengths by the ongoing expansion that they carry almost no energy, a few electrons, a few positrons, a few neutrinos. The occasional fundamental particle that has somehow avoided any interaction since the beginning of everything, all of it drifting. And here is the strange, quiet quality of the dark era that I want you to feel. In this state, particles almost never meet. The universe is so spread out that the distance between any given electron and the next nearest particle is enormous. Even at the speed of light, a signal from one to the other would take timescales that dwarf every era we have described so far tonight. When two particles do happen to interact, which is exceedingly rare, they interact briefly, then drift apart again and continue their long solitary journeys through the expanding dark. There is no light, not because there are no photons. There are photons drifting quietly, endlessly stretched by expansion, but their wavelengths are so long and their density in space is so low that from any point in the universe, in any direction, there is essentially nothing to see. If you could somehow place a perfectly sensitive detector anywhere in the dark era and leave it running, it would register almost nothing, not because it was broken, because there is almost nothing to register. There is no structure, there are no stars, there are no galaxies, there are no black holes, there are no atoms in any conventional sense. Just particles adrift and space between them, expanding. There are no events. That is the phrase I keep coming back to. In the dark era, there are no events. Nothing happens that is different from what was happening 1 billion years earlier, or 1 trillion years earlier, or a Google years earlier. The universe simply exists and continues and stretches and cools and thins forever without meaningful change. That is the true end state of everything we have walked through tonight. Not a bang, not a rip, not a crunch, just a very quiet, very cold, very slow drift into a state that has no boundary, no observer, no rhythm, and no next chapter. I need you to sit with that for a moment, because that is the ending. That is what dark energy guarantees. That is where the timeline lands. In the final analysis, if our current physics is even close to correct. And now, I want to turn the whole thing inside out, because if you have followed me through tonight, if you have walked with me from the layer beneath the layer that Webb pulled out of the dark, through the fires of the stellar era, through the closing of star formation, through the dissolution of galaxies, through the vast, slow evaporation of black holes, all the way to the dark era at the very end, then something should have quietly clicked into place. Something the timeline itself does, if you look at it long enough. Look at the shape of what we described. Almost all of cosmic time is the dark era. Not most. Almost all, if you added up every second of every era we walked through tonight. The era of stars, the era of stellar corpses, the era of dissolving galaxies, the entire 10 to the 100th power year run of the black hole era, all of it stacked together. That whole enormous timeline is still less than a rounding error compared to the duration of the dark era, because the dark era goes on forever. It is not a chapter. It is what comes after all chapters have ended, and it has no closing page. Now step back. Look at where we are in that shape. We are near the beginning, not just at the beginning of the timeline. Near it, so near it, that on the scale of the full story, we are effectively at time zero. 14 billion years into an unimaginably longer history. It is the equivalent of standing at the very edge of a beach that stretches out beyond every horizon you can see, and calling that edge somewhere. It is somewhere, but everything else is elsewhere, which means that right now, tonight, at this quiet moment, we are living in the brightest, densest, most structured moment the universe will ever have. I want to say that again, because I want it to land properly. This era, the one you are alive in, is the brightest moment the universe will ever have. Stars are still forming. Galaxies are still whole. Light is still traveling across cosmic distances, and being caught by mirrors made of gold on small spacecraft orbiting small worlds around small suns. There is still warmth, there is still structure, there are still observers to observe. None of that is the default state of the universe. Almost none of the timeline contains any of it. The default state, the state that occupies almost all of cosmic time, is the dark era. The cold, silent, endless drift. That is what the universe mostly is, in terms of duration, and we are not in the dark era. We are in the small, brief, bright chapter at the start. That is what the layer beneath the layer Webb just found actually means. It is not evidence of futility. It is not proof that the universe is doomed and pointless. It is evidence of how much light there is right now, how dense this moment is, how full the universe is, in this specific brief chapter of exactly the things that will not exist for almost any of the rest of the timeline. Every one of those faint galaxies that Webb pulled out of the dark is a testament, not to the vastness of loss ahead, but to the improbable richness of the moment we happen to be alive in. Think about how strange that is. Out of all the epochs the universe could put a conscious being into, we ended up in the one where the sky is full, where stars still burn, where galaxies still exist as galaxies, where the light from ancient furnaces still reaches us in wavelengths we can catch, where a mirror made of gold, 1,000,000 miles from a small blue world, can pull faint smudges of ancient starlight out of the dark and add them to a growing map of what the cosmos contains. That is not a small thing. That is not a footnote to a tragedy. That is, if you look at it honestly, extraordinary. We are early. We are so early that the language of early barely applies. Every galaxy that exists tonight is a galaxy that will not exist in most of the future of the universe. Every star burning tonight is a star that will not be burning in most of the future of the universe. Every photon traveling across space tonight is doing something that photons will almost never do again in any meaningful sense after this brief, bright chapter closes. The dark era is what the universe mostly is. The stelliferous era, our era, is a small candle burning at the very beginning of an unimaginably long night. And we are here, right now, gathered around that candle. It is warm, it is bright, it is real, and somehow that is enough. I want to bring us home now, all the way back to where we started. Remember the galaxy from the first part of tonight's story, the one I asked you to hold in your mind. A single faint distant galaxy that Webb pulled out of the dark for the first time in the entire history of anyone looking up. A galaxy whose light left it more than 13 billion years ago, when the universe was still an infant, and traveled quietly through expanding space for longer than our sun has existed, longer than the atoms in your body have been arranged in the pattern they are arranged in now. That galaxy is still there tonight. Whatever it looks like now, in whatever moment its own local physics considers now to be, it is still there. Its stars are still burning, or its stars have already burned, depending on the era it currently occupies. Its light is still traveling. Some of that light, this exact instant, is still arriving at Webb's golden mirror, adding faint whispers of infrared to the ongoing survey of the cosmos. You are alive during the part of the timeline where that is possible at all. You are alive during the part of the timeline where a small blue world can orbit a small yellow star in a spiral galaxy that has not yet dissolved, and a species on that world can build a telescope and lift it into space and unfold its gold mirror in the dark and receive photons from a galaxy so far away that the light left it before there was a solar system to receive it. That happens exactly once, not for every era, not for most eras, not even for a meaningful fraction of eras. It happens during this small, brief, bright chapter at the very beginning of everything, and only during this chapter, and you happen to be alive right now. Whatever room you are in tonight, wherever you are listening from, whatever hour is glowing on your clock right now, the light from that galaxy is still reaching us, still arriving, still adding another faint layer to the growing map of what the universe contains. The universe is still glowing, the furnace is still lit, the candle has not burned down yet. Sleep well tonight. There is still light, there is still warmth, there is still structure to be alive inside of. There is still time. In the only chapter of time when any of this is possible, you are here. The universe is glowing, and you get to be here while it does. Rest gently. The candle is still burning. You are inside the layer that has light in it.